All right, so in this video, we're going to take a look at a couple examples showing that limits do not exist. And so from the first video, we talked about how if you have multivariable limits, for it to exist, it's got to be the same thing for all different ways of approaching that point. Okay, so every single way to approach 0, 0 along this surface has to be the same limit. And so to show something doesn't exist, we're actually just going to show the contradiction. We're going to show that you get different things depending on the path that you approach this point along this surface. Okay, so one of the more common techniques is by just starting off letting y equal mx. All right, now I say y equal mx because that's a line. It's a linear function, m being the slope, and it does go through the point 0, 0. We always have to make sure what we pick goes through the point that they give us. So if y equals mx, then I'm going to go ahead and replace all of the y's up here with mx. So in doing this, we're going to have a limit. We're going to have an x cubed times mx over 2x to the 6th plus mx quantity squared. And much like the last example, we don't have any y's, and so it's perfectly reasonable just to write x approaching 0 now. Now, if you simplify this, which it does simplify quite nicely, we're going to get mx to the 4th. And in the denominator, you've got an x to the 6th here and an x squared here, so you can take out an x squared. So if I take out an x squared, that's going to give us 2x to the 4th plus m squared. Now, the x squared and 2 of these go away, leaving us with the limit as x approaches 0 of mx squared over 2x to the 4th plus m squared. And if we do go ahead and we evaluate now at 0, we get a 0 over an m squared. So we get a 0. Now, that alone tells us absolutely nothing. That just says as we approach this point on this path, on this surface, we're going to have a z value at 0. Okay? So now let's keep moving. Let's go ahead now and let y equal k x squared. So I went from a linear function that goes through this point to now a quadratic that goes through this point. So I'll do the same thing as before. Limit as x goes to 0. We'll have our x cubed and our kx squared over 2x to the 6th plus kx squared squared. And so now let's simplify it a little bit. That's going to be a kx to the 5th over 2x to the 6th plus k squared x to the 4th. So now I can factor out an x to the 4th. So our kx to the 5th, I'm going to factor out the x to the 4th, leaving with 2x squared plus k squared. With this dividing off here, leaving me with just a single x on top. When we evaluated 0, this would be k times 0 divided by 0 plus k squared. So 0 over k squared, which would be 0. So this one also ends up at 0. All right, so now let me go ahead and slide this up a little bit, and let's do another one. Let's go ahead and let y equal cx cubed. And just to remind you again, so far we've approached two different paths, actually infinitely many paths considering we have different slopes and different coefficients, but regardless, we're getting the same number. Now again, this doesn't mean since we got the same number that the limit is going to exist at 0. We still have infinitely many more avenues to check. So I'm going to continue down now and go from a linear to quadratic to a cube. And again, just do the same thing. We're going to have the limit as x approaches 0 of x cubed cx cubed over 2x to the 6th plus cx cubed squared. When we simplify, that's going to be a cx to the 6th over 2x to the 6th plus c squared x to the 6th. Now when we simplify this, limit as x approaches 0, cx to the 6th, we take out an x to the 6th, we're left with 2 plus c squared. And when these x to the 6th divide off, Now what you're going to end up with is a c over 2 plus c squared, which is actually now enough to say that the original limit does not exist. Now, why is that enough to say the limit doesn't exist? Well, first of all, sure, could this limit equal 0? Yes. If c is 0, then in fact we get another 0 for this whole thing, and we would have gotten 0, 0, 0, and it would have been inconclusive. But right now we're at the mercy of c. So depending on what c is, if c is 1, if c is 2, if c is 3, you're going to get different answers. And so because you're going to get different answers, not only from these two original, but from this one as well, we're solely dependent upon c. So the way we approach along this curve, depending on c, is going to tell us that we're going to potentially be getting different z values for this limit. Therefore, we've proven now that this limit doesn't exist, since, again, we're getting different values from it. All right, so this one we're going to work in a similar way, still showing that it doesn't exist, but I'm going to use a little bit of a different approach, one that you might find helpful depending on certain problems. And so, unlike using the y equals mx, y equals kx squared, y equals cx cubed, we're just going to approach along different coordinate axes. And so, if we want to approach along the x axis, and again, I say coordinate axes because us going through 0, 0, 0 makes good sense that the coordinate axes will all three do that. And so if we go through the x-axis or approach along the x-axis, we're going to have the ordered triple x, 0, 0. X can be anything it wants to be, but y and z have to be 0. And so if that's the case, then the limit that we need is going to be nothing more than the limit as x approaches 0. Right, x is approaching 0, and so we're about to come up with a function with only x's in it. So our x's are going to remain x's, our y's are going to become 0, and our z's are going to become 0. So that's going to be an x squared, 0, 0, x squared, 0, 0. So that's going to be an x squared over x squared, which of course equals a 1. Now that's approaching along the x-axis. If we want to approach along the y-axis, and alone, again, that tells us nothing. Alone, that tells us absolutely nothing. We've only approached one way of infinitely many, and it gave us a number. Great, but let's keep moving. So if we approach along the y-axis, we've got 0y, 0, and it'll be a limit as y goes to 0. Your y value is going to 0 up here, so that's where this comes from. In this function, x is going to be replaced with 0, y is going to stay itself, and z is going to be replaced with 0. So that's going to give us a y squared over y squared, which equals 1. Again, that doesn't tell us anything. In fact, these two being the same might suggest otherwise, but we need to keep going. Now we'll approach along the z-axis. So that's going to be 0, 0, z. Limit as z approaches 0. We're going to go ahead now and plug in 0 for x, plug in 0 for y, and leave z by itself, which is going to give us a negative z squared over a positive z squared, which is actually equal to negative 1. So because now the 1 does not equal the negative 1, we can clearly, definitively say that this limit does not exist. All right, so the last thing we'll talk about in this section is continuity, which comes on the coattails of us studying domain in the last section, which is a nice connection as well. So in R2, if you guys remember, the definition of continuity from Calc 1 was that the limit as x approaches a of f of x equaled f of a. So for a function to be continuous at x equals a, the limit had to equal the point. The limit had to exist, meaning the left and the right had to equal the same thing, and the point had to exist, and the two things were equal. In Calc 3 now, dealing with R3, it's going to be pretty similar. We're going to have a limit as xy approaches ab of f of xy, and that's going to need to equal f of ab. So the conditions that were talked about here apply this exact same way over here. We just clearly have now a little bit of some different notation because we're dealing with higher dimensional things. So we're going to take a look at this first one here, and we're just going to say, okay, where is this thing continuous? So the function I want to look at is square root of x minus y. Where is this thing continuous? Well, First thing that comes to my mind is that underneath this radical, we can't have a negative. So that says that x minus y must be bigger equal 0, which also says that x must be bigger equal y. So now when it comes to expressing where this function is continuous, we'll do so in a similar manner as to what we did with the domain. We're going to graph this. And so looking at our xy plane, the line y equals x looks like this, where it goes through the origin right here, even though it doesn't look like mine did. So it goes through the origin. It is going to be a solid line because of the or equal to, so it's going to be solid. And then the places where x is bigger equal y would be the region below that line. So if I go ahead and shade this in, this is where the original function here is going to be continuous. So again, kind of follows up nicely with the whole idea of us studying domain in the last section, and hopefully you can apply those same techniques and the idea of continuity not only from this definition but from Calc 1 to whatever it is you might encounter.